topic of this lecture is important theorem part 2 of Riemann integration. We will cover three theorems, theorem number 1, theorem number 2 and theorem number 3 in this lecture. Let us see the statement of first theorem. If f is Riemann integrable on AB, where C is any point between A and B, then f is Riemann integrable on AC and f is Riemann integrable on CB, and integration of f over AB will same as integration of f over AC plus integration of f over CB. That what we are doing, we are dividing the interval A and B with some point C. So f is Riemann integrable on AB, then it will be Riemann integrable on AC and it will be Riemann integral on CB, and this will also hold. So that we are going to prove. So for that, let us see the proof. As f is Riemann integral on AB, so f is continuous almost everywhere on AB. That we know. So because of this, the set E of points in AB at which f is not continuous is of measure 0, because f is continuous almost on AB. But this implies that if we take intersection of E with AC, then this set will also of measure 0. And because of this, it means that f is continuous almost everywhere on AC, and this implies that f is Riemann integrable on AC. Similarly, we can prove that f is Riemann integrable on CB. Now let us prove this thing. These two things we have shown. Now let us see these things. For that, let sigma is any subdivision of AC and tau is any subdivision of CB. So what we are doing, we are taking A and C. For this, we are taking the subdivision sigma, and for this C and B, we are taking the subdivision tau. Then sigma union tau will be a subdivision of AB, that is very clear, whose component interval are the component interval of sigma together with the component interval of tau. That will happen. Because of this, the lower sum of f over sigma plus lower sum of f with respect to tau, that will be lower sum of f with respect to sigma union tau, and lower sum is always less than equal to lower integral, that we know. But f is Riemann integrable, so these two will be equal. So here we obtain that lower sum of f with respect to sigma plus lower sum with respect to tau is less than equal to a to b f. Because of this, because f is Riemann integrable, so these two are equal. Now here in this expression, taking tau fixed, this tau is fixed, and taking least upper bound on the left over all sigma, because this always holds. So if we keep on changing the sigma, and if we take the least upper bound of on all sigma, we get integration a to c f plus l f tau, that is less than equal to a to b f. Now from here, we take the least upper bound over all tau, because this hold for any tau. So if we take least upper bound, we get a to c f plus c to b f, that is less than equal to a to b f. So this is the first inequality we have proved. It is very easy. Similarly, in place of lower sum, if we start with the upper sums, we get that upper sum of f with respect to sigma plus upper sum of f with respect to tau, that will be upper sum with respect to sigma union tau, that will be greater than equal to upper integral of f over ab, because we know upper sum is always greater than equal to upper integral. But this too is equal because f is Riemann integrable. So finally we got this. Now here again, the taking least greatest lower bound on tau and sigma one by one, we obtain, as we have seen in this case, but the case is just reverse in this case, that a to c f plus c to b f is greater than or equal to a to b f. And because of this and this together by 1 and 2, we obtain that these two are equal, that a to c f plus c to b f is equal to a to b f. So by this way, we have proved this part also. Now let us see the next theorem, that is also easy. If f is Riemann integrable over ab and lambda is any real number, then lambda f, this new function, is also Riemann integrable over ab, and integration of ab of lambda f is lambda times a to b f, that we are going to prove. So let us see the proof. Now see, lambda can take different values. If lambda is equal to 0, then theorem is clear, as both sides are equal to 0. These two sides are equal to 0. So this is obvious case. Now let us take lambda is greater than 0. Then, because lambda f is continuous at every point where f is continuous and f is Riemann integrable, which is given to us, it means f is continuous almost everywhere. So this implies lambda f is also continuous almost everywhere on AB. But this implies that lambda f is Riemann integrable over AB. So that part is proved. Now, as lambda is greater than 0, so if we take any interval j which is contained in AB, this equality holds, that is supreme value of lambda f over j is equal to lambda times supreme value of f over j. But this implies if we take any subdivision sigma of AB, then this upper sum of lambda f with respect to sigma is equal to lambda times upper sum of f with respect to sigma. So that will hold. Now, taking the greatest lower bound GLB both sides across sigma, we have this sides, from this side we get a to b lambda f integration, that is equal to GLB of u upper sums lambda f over sigma, that will be lambda times, from this lambda times GLB of u f sigma, but that implies that this is equal to lambda times a to b f. So from this first and last, we have shown that a to b lambda f is equal to lambda times a to b f when lambda is greater than 0. Hence, we have proved that theorem is true when lambda is greater than 0. Now, let us take the another case. Now, for any interval j, we know that upper supreme value of minus f over j, that will be infimum value of f over j, and it's negative, that is minus of infimum value of f over j. So because of this, when we find the integration a to b of minus f, that will be GLB of upper sum of minus f over sigma by definition, that will be GLB of minus of lower sums of f over sigma because of this, and that will be minus times LUB of lower sum over f of sigma, but by definition this is equal to a to b f, minus of a to b f. So in this case we have just proved that these two are equal. So we have written over here that a to b minus f is minus times a to b f. Now this will be used in case when lambda is equal to 0. So now take the case lambda is less than 0. Then take mu, which is equal to minus lambda, that will be greater than 0. Why it is greater than 0? Because lambda is less than 0. So minus lambda is greater than 0. That's why mu is greater than 0. So by 2 and 1, a to b lambda f, that will be simply a to b minus of mu f, because lambda is equal to minus mu from this relation, and this is equal to minus we can take out because of this, because of we have proved this, so minus is taken out. This is a to b mu f, and then as mu is positive, so mu also we have taken out, so a to b f, and minus mu because of this equal to lambda. So it is equal to, we have proved that A to B lambda f, where the lambda is negative. This is also same as lambda times A to B f. So in this way, we have proved the three cases when lambda is equal to 0, that we have shown that theorem is true. Lambda is greater than 0, that we also shown it is true. And lambda is less than 0, in this case also we have proved that theorem is true. So let us take the next theorem, that is also easy. If f is Riemann integrable over AB and g is Riemann integrable over AB, then f plus g is also Riemann integrable over AB, and a to b f plus g is a to b f plus a to b g. So that is the statement that we are going to prove. So let us start proof. As f is Riemann integrable over AB, g is Riemann integrable over AB, so f and g are continuous almost everywhere on AB. Hence, the set EF and EG of points at which F and G respectively are not continuous are both of measure 0. Why this is so? Because F and G are continuous almost everywhere on A and B, A to B. Hence, the set EF union EG is of measure 0. So we have obtained that EF and EG is of measure 0. Now if we take any point X which lies in AB but not in this set, that is X belongs to AB minus union of EF and EG, then FG and hence F plus G are continuous at X. Why this is so? Because this X does not lie in EF, it does not lie in GG. So F and G are continuous, so F plus G is also continuous at X. It means that this simply implies that f plus g is continuous at most every point in AB. That is, f plus g is continuous almost everywhere on AB, because at every point x which does not lie in these two sets, f is continuous, f plus g is continuous. So we obtained that f plus g is Riemann integrable. So this first thing we have proved, that f plus g is Riemann integrable. Now let us see the second part. This we have to prove. Let j is any interval in AB, and if we take y is any point in j, then the value of f at y plus value of g at y, that will be less than or equal to, it should be less than or equal to supreme value of f over j and supreme value of g over j, because y is any arbitrary point. This is your j and y is any point. So the value of f at y plus g at y, that will be less than or equal to supreme values of f and g. Hence we obtained that because this inequality holds for any y, so supreme value of f plus g over j, that will be supreme value of f over j plus supreme value of g over j, that will hold. And because of this, therefore, any subdivision sigma we have, because of this inequality we have, if we take any subdivision, then integration a to b f plus g, that is less than or equal to, it should be less than or equal to upper sum f plus g over sigma, that is less than or equal to upper sum, this should be less than or equal to upper sum with respect to f over sigma and upper sum with respect to g over sigma. That will hold because of this. But as f is Riemann integral over AB, so given epsilon greater than 0, there is a subdivision sigma 1 of AB such that this upper sum with respect to sigma 1, that is less than equal to lower sum with respect to sigma 1 plus epsilon by 2, that we have seen in the previous theorem, and that will be less than equal to a to b f plus epsilon by 2, because our upper sum is always less than equal to upper integral. But as g is Riemann integrable over AB, there is a subdivision sigma 2 such that this inequality hold, as we have seen in case of f. Now if we take sigma is equal to sigma 1 union sigma 2, then upper sum with respect to sigma, that will be less than equal to upper sum with respect to sigma 1 because sigma is refinement, and this is less than equal to a to b f plus epsilon by 2. Similarly, upper sum with respect to g on sigma, that will be less than equal to this, and that will be less than equal to a to b g plus epsilon by 2. So from 1, because of this is 1, we have that integration a to b f plus g is less than equal to integration a to b f plus a to b g plus epsilon. But as epsilon is arbitrary, this proves that integration of f plus g over ab is less than equal to a to b f plus a to b g. Now, as f and g are Riemann integrable functions, so replacing f and g by minus f and minus g, because these two are also Riemann integrable, we get a to b minus f minus g is less than equal to a to b minus f plus a to b minus g. But this gives us that minus of a to b f plus g, taking minus common, is less than equal to minus of in bracket a to b f plus a to b g. Now if you multiply both sides by minus 1, the inequality gets changed, reversed, and we get a to b f plus g is greater than equal to a to b f plus a to b g. And we have shown that this is greater than, and earlier we have shown this is less than. This is less than this, that we have already shown. Because of this 2 and 4, so what is 2? 2 was this was 2, and the fourth one is this. Because of this, we have that these two are equal. So by this way, this theorem is proved. So thank you very much. You can find the link of this PPT in description box. Thank you.